All right, welcome to AP Calculus Lecture 3.8 and 3.9a. 3.8 just is an informational lecture. We're not going to work any problems. I just want you to know, in case in college calculus you have to deal with this, you at least have been exposed to it, but it's called Newton's method. And if you could print out these lecture notes that I have for you, and on the test I really only want you to know what Newton's method is. You aren't going to be working any problems with Newton's method. It is not on the AP test. So when, years and years ago I just quit teaching it other than what it is. But what Newton's method does is it uses derivatives to find approximate solutions to functions. And Newton's method is an iterative process, meaning that it does the process over and over and over again until it gets to a really close approximation of the answer. All right, so you get better and better approximations. And what are we trying to approximate? Well, it's where f of x is equal to 0. Where does the function cross the x-axis? Okay, so finding the exact solution of f of x equals 0 is really difficult for most functions. Now, we kind of focus on lines and quadratics, right, where we have tools to set something equal to 0. You can factor to use the quadratic formula. But honestly, most mathematical functions aren't really nice and easy, well-behaved functions to deal with, like lines and parabolas. They're crazy, curves that are to all sorts of different degrees, and we just don't have a good way of setting them equal to 0 and solve. But it is easy to find f of x equals 0 for lines. So with Newton's method, let's say we have this curve here that I've drawn out. We just make an initial guess of where f of x, what x value would give us a y value of 0. And then we find the tangent line at that initial guess. And then we can see where that crosses the x-axis. And we repeat that process until we get a y value that's really, really close to 0. So you don't have to memorize this formula or anything like that. But you would just keep doing it. So we start with that x1, and then that gives us a place to start with x2. So that would start here, see where that crosses the x-axis. And you just keep doing it again and again. So really all I want you to know is that Newton's method is a way of approximating where the function crosses the x-axis, where f of x equals 0, using tangent lines. All right, so that's it for Newton's method. Today's main lecture, 3.9a, is called Tangent Line Approximation. And another word for that is linear. So linear meaning line approximation. All right, so the tangent line emulates a curve, and the reason I'm writing like this is that we're going to draw a graph over here. I'll go ahead and give myself some space for that. Emulates a curve at points near C. So I'll put C on the graph in a minute. So therefore, the tangent line is a good approximation for f of question mark. All right, what do I mean? Let me draw this out. Let's say we have a point C right here. And f of C right here. So we have this point. And it's part of a curve. So this, all right, let's say that is f of x. Okay, so let's say that a point near C, let's say, is right here. And we'll call that point question mark. And that is f of question mark. So what you're doing with tangent line approximation is you are, let me put this in a different color. So let's say we find the tangent line, the equation of the tangent line at the point C, and it looks like that. Then we can plug our value question mark, whatever that is, into that line and get a really good approximation because it's pretty close to this point f of question mark. So we get an approximation or an estimate of f of question mark that's really close, because lines are easy to deal with. Okay, so the example that I want to do for you, and I'm probably not going to be able to fit it in on here, but the example I want to do is number 2 on page 226. So if you open your book to that point, you can see that you have a table there. All right, I'm going to go ahead and kind of pre-fill out this table. So we have x, f of x, so our actual y value, and then t of x, which is our tangent line approximation of the value. So let's say we have 1.9, and leave a little space because we'll go out to about 4 decimal places. 1.99, 2. So 2 is our actual, that's our value on our previous graph. That would be C. And then 2.01. You might remember doing a table like this all the way back in our first lecture in chapter 1, our first homework assignment, and then finally 2.1. So we're only 1/100th away from 2 here and here, but we get all the way to a 10th there. So our equation here is f of x is equal to 1 over x squared. So our point x is 2, f of x would be 1/4. Okay, that's given to you, so 0.25. Now we can go ahead and plug in. So for example, what's f of 1.9? That's 1 over 1.9 squared. So if you put that in your calculator, you would get, and you're rounding here, but 0.277. So let's put that in, 277. And you could do that for 1.99, 2.01, 2.1, but let me go ahead and fill that out. So for 1.99, it would be 0.2525. For 2.01, 0.2475. And then 0.2268 for 2.1. So we've got the actual f of x's for these points surrounding 2. Now let's get a tangent line equation. So f prime of x, so first of all, let me rewrite, let's do this a little easier. F of x, let's rewrite that as x to the minus 2. So f prime of x is minus 2x to the minus 3. So that's negative 2 over x cubed. So the slope, our tangent line slope, we're going to plug in 2 for that, 2 for x, right? Our x value is 2. So we have 2 and 1/4. So that would be negative 2 over 2 cubed. That's negative 2/8, which is negative 1/4. So that's our tangent line slope. So now we can get t of x, our tangent line equation, using these 2 points, x and y. So I would have y minus y1, which is 1/4, is equal to the slope, negative 1/4, times x minus 2. So solving for y, because that's what we're going to be, t of x is what we're going to be putting in here. It'd be, I'm going to move the 1/4 to the other side. That's equal to negative 1/4 x plus 1/2. Excuse me here. Plus negative 1/4 x plus 1/2. So that is going to be y equals negative 1/4 x half plus 1/4 plus 3/4. So let's start filling this out. So y of 1.9, and it's really, this is our tangent line equation, so let's call it t. T of 1.9 is going to be negative 1/4 times 1.9, I'm just plugging it in right here, plus 3/4. All right, when you do that, you get 0.275. So that's a pretty good estimate of 0.277, right? It's within 2/100ths. And then if we did 1.99, that's negative 1/4 times 1.99 plus 3/4. And if you plug that in, you actually get a match up to 4 decimal places, 0.2525. And then if you plug in 2 here, you're going to get 0.25. So that's because you share a point on the curve. That's the point of tangency, so it's going to be exactly the same at 2. And then 0.24, if you plug in 2.01, I won't do them all, 2475. It also matches to 4 decimal places. And then 0.2250 at 2.1. So you can see that at points near the point of tangency, you get a really good estimate. So if 1/100th away, you're up to 4 decimal places of accuracy. You know, that's a really good estimate as long as you're close. Now you get further away, a whole 1/10 away, then you start to deviate some. And if we did 2.2 and 1.8 on that end, our estimates would get worse and worse. But like I said on the previous notes, near the point of tangency, the tangent line is a really good approximation for the actual curve. Okay, so you'll have a couple of homework problems where you have to fill out that table. So you can just refer back to this example, and that'll be numbers 3 and 5. Okay, next, a very similar topic. It's called differentials. All right, so I'm going to do another graph over here to the right. So I'm just going to keep my notes to the left. At values close to x, delta y is approximately equal to dy. We also have dx is equal to delta x. So if you have dy dx equals f prime of x, then dy is equal to f prime of x times dx if we just multiply both sides by dx. So dy is called the differential of y. So it even the letters kind of match. Differential of y. Dx is called the differential. I bet you can get this. Of x. So let's draw this out. So I'm going to use a nice big parabola here. So that's f of x, just this side. So let's say we have a point x. All right. And its corresponding y value is f of x. Okay, now I'm going to have to, in order to show, I'm going to have to pick a delta x. Let's say that this point is x plus delta x. And the difference between those 2 points is delta x. All right, so that would be up here. And then this is f of x plus delta x. So the difference between these two is called delta y, the change in y. Now if we were to draw a tangent line, so I'll do this in red. So let's say we have a tangent line like that at the point of at x, come up with a tangent line equation. Then what we had our estimate there of x plus delta x right there. The difference between those two is called dy. So again, just like the other one, dy is an estimate for delta y, okay? And at points near x, you get a better estimate finding dy, okay? But it's basically the same thing that we just did, just with some different words. So the actual change in y we call that delta y, and that's equal to f of x plus delta x minus f of x. All right, that minus that. You've seen that before. the estimate of our change in y is dy, and that's equal to f prime of x dx. All right, that's our estimate. So we're going to work a problem next where we compare delta y to dy using differentials, using this technique of getting an estimate, and see how close they are. All right, and the example we're going to do is number 8 on page 226. So number 8, our function y is equal to 1 minus 2x squared. They give us that our point x is equal to 0. And delta x, which is also equal to dx. Now delta y and dy are not equal, but delta x is equal to dx. That is negative 0.1. So first of all, we want to find delta y. And we know that's equal to f of x plus delta x minus f of x. So f of x plus delta x that's going to be f of, we know x is 0, 0 plus negative 0.1 minus f of 0, right? X is 0, and delta x is negative 0.1. So delta y is equal to f of negative 0.1 minus f of 0. All right, so that's going to be, we're going to plug things in now. 1 minus 2 times negative 0.1 squared, right? I'm plugging into the equation, minus 1 minus 2 times 0 squared. Okay, that's f of 0. That's f of negative 0.1. Okay, so delta y is equal to 1 minus, and this would be 0.02, minus 1 minus 0, so minus 1. So the 1's cancel out and you get negative 0.02. That's our actual change in y. Now I want to compare that to dy. So we know that for this function here, dy dx, the derivative, or f prime of x, is equal to minus 4x. So dy is equal to minus 4x dx. Multiply both sides by dx. So that's going to be minus 4. X is 0. And then dx is negative 0.1. Well, that's just 0. So delta y is negative 0.02. dy, excuse me, not dx, dy is 0. So that's pretty close. So our estimate is pretty good, because those two numbers, they're within 2/100ths. All right, so, and negative 0.1 is just a tenth away from 0, so you should get a pretty good estimate there. All right, so that's example number 8. That's going to help you work number 7 and number 9 on the homework. So let's do one more example and we will be done with this lecture. Our last example is example 12. Still on the same page. And we just want to find the differential dy. And for number 12 it says y is equal to 2x to the 3/2. Now you're going to be happy with how easy this is. So we're going to find dy dx. That's going to be 3/2 times 2. That would be 3x, right? 3x. And don't forget to subtract 1 from the exponent. So 3x to the 1/2. So multiply both sides by dx. You'd have 3x to the 1/2 dx. And that is our differential dy. That's all it's asking. It's just asking you to take the derivative and multiply by dx. So the homework from this section is on page 226, all of them. We're going to do 3, 5, 7, 9, 11, and 13. I guess I could have just put 3 through 13 odd, couldn't I? Now 3 and 5, just looking at these, 3 and 5 are, you refer to example 2, you're just making a table here. And you also want your calculator to be in radians here for number 5, so be careful there. Then 7 and 9, you're going to do like I did example 8. All right, you're going to find f of x, find f of x plus delta x, find the actual change in y, and then take the derivative and multiply by dx to find dy, and compare the two for 7 and 9. And then 11 and 13, you're really just taking the derivative there. So that's like the last example I did, number 12. So all of these answers are in the back of the book. So I don't think the back of the book answers will give you any trouble as far as simplification goes. And that's it for this lecture, and I'll talk to you on the homework solutions video.